Welcome back. This is lecture 3.1b. As you remember, we've just started the derivatives unit, and last time we talked about finding the equation of a derivative function. We have one loose end to cover from that objective, but then the bulk of this video is going to be about sketching and recognizing the graph of the derivative function using some intuitions about slope. First, the loose end. So yesterday we saw a definition of the derivative function that involved the difference quotient. It turns out there is a second way to define the derivative, a second way to find it, and you'll get the same answer every time, but for whatever reason, sometimes some people find this one easier for some functions, so I'm going to go ahead and show it to you. Pause the video now to copy this down. Once you have it copied down, and you need to focus on this formula, you don't necessarily need this graph because it should be earlier in your notes already. But once you have this formula down, pause to think about how it's similar and how it's different from yesterday's definition of a derivative. Great, so there's a number of observations you might have made when Edpuzzle asked you. Obviously, the major difference is that we're talking about A's, not H's, and the term of the limit is x approaching a, as opposed to h approaching 0. In my opinion, if there's one thing people get wrong when they start switching back and forth, they'll often end up with the wrong limit term. They'll say h approaches 0 or x approaches 0 with the wrong version of the formula. Otherwise, it looks pretty similar. We have two things with f on the top, only this time there's no x plus h, so there's just an f of x and an f of a. The idea is the same as last time, only instead of talking about the distance between x and another point, that distance was h, we're now just going to talk about two different points, and their x values are x and a. This limit is saying we take the slope, and we calculate the slope of these 2 points, and then we bring the second point closer and closer and closer to a. Obviously, we'll end up with the slope of a tangent line, and that's the derivative. So let's see this in action. I'm going to have you work out these 3 examples. You may notice they're actually the same examples as yesterday's video, but instead of using the limit of the difference quotient, we're going to use this alternate definition. I'll work the first one out with you so you can see what it looks like. I've got my original function, f of x equals the square root of x, and to find the derivative, which is f prime, we're going to take the limit of f of x minus f of a over x minus a. Of course, f of x is just the square root of x, so this limit will equal the square root of x minus the square root of a, all over x minus a. Now, I should have done this at the beginning, but you probably already recognized that my goal is to evaluate the limit, and I can't plug in x. Well, I can't plug in a, because if I put in a for x, that's what it's getting close to, we would have a minus a on the bottom. If you have a hard time thinking about this with the a there, imagine a number instead. If there was a 2 here and this said x minus 2 on the bottom, we wouldn't be able to plug it in. So I'm going to continue simplifying. A conjugate is the next step. And when I FOIL out the top, I get the limit as x approaches a of the square root of x squared minus the square root of a squared, all over x minus a. Remember to put your parentheses around the first binomial, and it's being multiplied times the square root of x plus the square root of a. Of course, on the top it simplifies, and it turns into the binomial x minus a, which we can then cancel out. And remember that when you cancel, it leaves a 1 in its place. So we now have a limit that we can evaluate. We can just plug in a, which is the term of the limit. We would plug it in right here for x, and we would get 1 over the square root of a plus a, the square root of a, sorry. Now, notice this is where I stop writing the limit, because at this stage I actually plugged in a for x. X is the term of the limit here, not an h, so the x's go away by the end. And we end up with 1 over 2a. Sorry, the 2 times the square root of a. Now, the good news is that's basically what we ended up with when we did our example in the last video. In fact, if you flip through your notes, I have mine here, you can see the work that we had. But the weird thing is, our answer in this example has an a in it and not an x in it. Your book rationalizes this by saying that really you're meant to have a particular point in mind, and you're then supposed to plug in that number for a. But to me, it's always been a little bit frustrating that you end up with an a here when you really are supposed to have a function with an x. So you would then convert it if you really just wanted to write the derivative function, and you would just write this as an x value instead. Now, aside from that kind of weird, confusing thing at the end, some of you may find this work more straightforward than the work where we had to actually FOIL out or deal with the x and the h inside of the square root. Go ahead and try this new method for the next two examples. When you hit play, I'll show you the answers. Great, so let's talk through the first one. And I'm going to kind of just talk through the steps because this is still unfamiliar for some of us. You set up the limit, and then you identify f of x and f of a, which really just means plugging in x and a to the original function and then putting them into your fraction where they belong. And now our goal is to be able to somehow cancel out that bottom term. And to do that successfully, you have to remember a formula from Algebra 2, which is the difference of cubes formula. And there's also a sum of cubes formula, which is pretty similar, so brush up on that if you need to. But if you did remember that formula, the canceling happens right away, and you're left with this nice, simple polynomial. And then we can now evaluate the limit by plugging in a. Think of it as a number if you're struggling with this, because there's no discontinuity, there's no problem, there's no zero on the bottom. So I just plug in a, and it becomes a squared, and a times a, and a squared, which is really just 3a squared. And again, if we reference our notes from before, that's the same answer we got with the other formula, only the work looked pretty different. This is a great example of a time when this second alternate definition seems like it's a lot shorter, and that's a benefit to us. If you haven't already, work out the last one, and then I'll show you the answers for the last one. And here we go. Notice that when I canceled out a minus x and x minus a, they turn into a negative one, which leaves a negative at the top. Pause the video if you need more time to look at this work. Otherwise, we'll move on. Cool, so we're done with algebra for a moment. Time to shift gears, and we're going to talk about the graph and some intuitions. This is the same graph that we talked about in last night's video. We had an original function, which is in blue. It's a parabola, it's facing down. And we went through this parabola using a tangent line, and we first estimated the slopes at some different points, and then we actually calculated the equation of the derivative after estimating them. The tangent line is in green, and the derivative that we're actually interested in is now graphed on the same set of axes, and it's this red line right here. You should recognize the function. Go back and check your notes if you need to. What would you say if I asked you, how are the graphs related? How are the graphs of f of x and f prime of x related? So there are a lot of correct things you could have said. You may have noticed that the original function was a parabola. Its degree is 2, whereas the derivative is linear and its degree is 1. You could have noticed that the original function had 2 roots and the derivative only has 1. You could have noticed that the maximum of the original function has the same x value as the 0 of the derivative function, and a lot of other things, frankly. I'd like you to hone in on 3 particular observations that are going to be really essential. So we're going to actually draw a little table. If you would set up a space on your notes so that you have a column for original function and a column for the derivative function, and then using the graph that you see on the screen, talk to me about what would happen to the derivative when the original function is increasing. And to be really specific, increasing is when the y values are getting higher. Look at the blue function. Find the part of the function where the y values are increasing. What do you notice about the derivative function? If you were looking closely, you would realize that on that region of the graph, we're talking about this graph increasing up to x equals 3, so before x equals 3. Well, before x equals 3, the original function is increasing, and the derivative function's y values are positive. We could say the function is positive, although really when we say that, we're talking about its y values. And an easier way to see that is that this function is above the x-axis in the same region of the graph as the region where the original function is increasing. How about this one? What do you notice about the original function on the part of the graph where the derivative function equals 0? In other words, when you see the x-intercept of the original function, when you see the x-intercept of the derivative function, what happens to the original function? Right, this is the one that I just talked about. When the derivative function has a 0 or an x-intercept, the original function has a vertex, in other words, a maximum or a minimum. You can probably guess the last connection that I'm going to ask you to see, which is what happens when the original function is decreasing? What happens to your derivative function's graph? Right, so the original function is decreasing when x is greater than 3. It's this right-hand side of the graph. And what you notice is that on the right-hand side of the graph, the derivative function is negative. In other words, the y values, the line is below the x-axis. These relationships will hold true for every original function and derivative function. They're going to help you sketch some graphs. Before we move on to that practice, though, notice what's not in this table. We don't have a connection for when the original function has a root or a 0. This original function does. It has two, in fact, one right here and one right here. But at these points, nothing special happens to the derivative. Now, at the root or 0 of the derivative, there's sure something special that happens to the original function. So the relationship is a little bit unbalanced. Make sure that you have these relationships down in your notes, and we're going to use them in just a sec.